Hello everybody, this is the second lecture of week 10 and we're going to carry on with hypothesis tests, and we're going to discuss a few things in hypothesis tests now that you did not see in confidence intervals, and they really aren't part of confidence intervals, they are parts of these tests. And we start with something called hypothesis test errors. Basically, with any hypothesis test, there's always a possibility of making an error, and there are basically two types of errors called type 1 error and type 2 errors, imaginatively enough. The type 1 error is that we mistakenly find an innocent person guilty. So this is basically, I'll define it more clearly down here, we reject H naught when it's actually true. So H naught in the judicial system is that people are deemed to be innocent. If we mistakenly find an innocent person guilty, then we've rejected H naught when it's actually true. And that's a bad thing. So type 1 error in the judicial system is to be avoided. The type 2 error is that we fail to find a guilty person guilty. And we'll see down here that means that we fail to reject H naught when it is actually false. Okay. So again, H naught is that a person is innocent. If that is false, then they're guilty. And if we fail to find them guilty, then we've made a type 2 error. And then basically here are the formal definitions. And basically the probability of a type 1 error is alpha. And we get to choose what alpha is. So basically you want to choose alpha to be small. But the problem is that there's another probability of making a type 2 error, which is called beta. And if alpha is small, beta tends to get bigger. And vice versa, if beta is small, alpha tends to get bigger. So you don't want to choose alpha to be too small, because then your probability of a type 2 error increases. Nor do you want to choose alpha to be too big, because then your probability of a type 1 error increases. So there's a balancing act. And basically alpha around 5 to 10% is usually found to be pretty good. So these two errors are not equivalent, nor are they complements. So one is not one minus the probability of the other thing. But like I mentioned, as alpha decreases, beta tends to increase. So we choose alpha small, usually 5 or 10% has been found to be reasonable. Okay, so let's illustrate this with an example. Let's suppose we have two girders being considered for a bridge project. Currently, girder number 1 is the standard and is an acceptable product. It gives reasonable levels of safety for the bridges. But type 2 might be acceptable, and since it's cheaper, it should be adopted. But we don't know so much about type 2 yet, so we want to check on the fatigue life of the two types of girders first. And if we would really only want to choose type 2 if it showed at least the same safety level as type 1. We don't want to sacrifice safety for cost. So to decide, we do fatigue testing on both girders, both types of girders, and record the number of cycles to failure. So the question here is, what hypothesis should we be testing and why? And in the context of this question, what is the type 1 error and what is the type 2 error? Okay, so let's let mu x1 be the mean fatigue life of girder 1. And we know that that's the current standard. And let's let mu x2 be the mean fatigue life of girder 2. And we know that that's a cheaper alternative. So what hypothesis should we test? Well, we could start by saying, okay, well, let's try this hypothesis. Set H naught to be that mu x2 is greater than or equal to mu x1. And that basically is saying that by default, we're assuming that the girder 2 has a stronger or longer fatigue life than girder 1. And then our alternative is just the opposite of that the second girder has a shorter fatigue life than girder 1. So this is a worse girder. The problem with this particular setup is if for example, I go out and collect some data, and suppose the fatigue life of x2 does turn out to be longer than H naught, then, does turn out to be shorter than H naught, then I reject H naught in favor of this. And if I do that, then I conclude that girder 1 is better and I keep using it. But the problem is that if for example, my X bar for girder 2 is bigger than for girder 1, then I will not be able to reject this, but I can never accept H naught. So even though it indicates this, the test doesn't prove this. So if I fail to reject H naught, I haven't proven that this is true, so I still have to use the girder 1, because I still don't know whether x2 is bigger. Okay? So in other words, this test does nothing. If we fail to reject H naught, we still continue with girder 1. If we reject H naught, we still continue with girder 1. So there's no change here. So in other words, we want to test actually reverse this. We're going to assume initially that girder 2 is worse than girder 1. And therefore, if we fail to reject H naught, we carry on with girder 1 as before. We are only going to choose girder 2 if it turns out to be better. It's proven to be better than girder 1. Okay, so we only choose this if we prove it to be better. And if we reject H naught, then we can go to girder 2 because we've shown that it's safer as well as cheaper. In this context, type 1 and type 2 errors are as follows. The type 1 error is that we reject H naught even though it is true. And there I'm concluding that girder 2 is better even though it isn't. And this one is bad. So we should choose alpha to be small. We don't want to use girder 2 if it isn't better. And type 1 error is saying that we've rejected H naught, we've found that girder 2 is better when it actually is not. Okay, so we want to avoid that. So we should choose alpha to be small, but again, we can't choose it to be too small. Basically, if we choose alpha to be 0, we'll never do anything because the confidence interval becomes infinite. A type 2 error is failing to reject H naught even though it is false. In this particular case, okay, so I failed to reject H naught, so it's false. That means that mu x2 is bigger than mu x1, okay? So basically it means that I'm going to stick with girder 1 even though girder 2 is better. Well, this is all right because girder 1 is currently acceptably safe. Girder 2 is actually a little bit safer and cheaper, but we're not sacrificing existing safety in this particular decision. So type 2 error is less bad than a type 1 error here. So for this particular problem, I would choose alpha to be 1 to 5%, that sort of thing, so quite small. Okay, another example, if the random variable x follows a normal distribution with unknown mean mu of x, but known variance. So we know what the variance is. That means we're going to be talking about z in this calculation. And we wish to test whether or not mu x is equal to some prescribed value, mu naught. Then what are our hypotheses and what are our what is our rejection criterion? Okay, so we have unknown, that should be an N on there, unknown mu of x, but we know sigma x, so we're going to be using z as I mentioned. Our hypotheses look like this. So our null is that mu x is equal to mu naught, and we're trying to test whether or not, so basically our alternative is that mu x is not equal to mu naught. If we fail to reject H naught, we say that mu x could be equal to mu naught, but more importantly, if we do reject H naught, then we conclude that mu x is not equal to mu naught. And this is now a two-sided test because we're going to reject H naught if we're far enough away either in the positive direction or in the negative direction. Okay? So our sentence becomes the following. Reject H naught if our test statistic, something equals something minus something over something. And the something on the left-hand side we now know is z because we've got a test on the mean with sigma known. And on the right-hand side, the first something is their estimate of mu x, which is x bar. The second something is the mean of this estimate according to H naught, which is mu naught. And underneath, we got standard deviation of x bar, which we know is sigma x over root n. So this test statistic becomes x bar minus mu naught over sigma x over root n. And we're going to reject this if our test statistic is either less than minus z alpha by 2 or greater than plus z alpha by 2. So this not equals means we look in both directions. Less than a negative value or greater than a positive value. And these values are now evaluated at alpha by 2. So that the area between them altogether is 1 minus alpha. Okay? So minus z alpha by 2 is over here. Area below that is alpha by 2. Plus z alpha by 2 is over here. Area above it is alpha by 2. And we're going to reject H naught if our test statistic is either above here or below here. Okay, so one-sided tests, I guess I just go through the list here. We now have looked at a two-sided test, and here's our sentence, a little bit more complicated. It has two parts to it. One-sided test, if you have a greater than here, so h naught mu x is less than or equal to 10, and we're going to test mu x equal, 20, and we're going to test mu x equals 20 against the alternative mu x is greater than 20, so this is the one-sided test, and we're looking in the positive direction. And our sentence becomes we reject h naught if our test statistic something equals something minus something over something is greater than. The greater than comes from HA, so it's this thing here, then a positive value, and it's Z sub alpha or T sub alpha. Okay, so alpha here because it's one-sided, not alpha by 2. Okay, we use alpha. This thing here is always the claim under the null, so that's going to be the 20. That goes in here. And then underneath here, we got the standard deviation of whatever we put in here. The other one-sided test is when we have mu x less than 20. So the null would be mu x greater than or equal to 20, and we test mu x equals 20 against the alternative mu x less than 20. Everything else is the same, except now because we got a less than there, we put less here, and we're looking in the negative direction. So we get a minus sign here, and this is either z alpha or minus t alpha. So minus z alpha or minus t alpha at n minus 1 degrees of freedom. Okay, another example. Suppose that optimal transmission through a coupler occurs when the coupler thickness is greater than 4 millimeters. You suspect that you're getting suboptimal transmission on average. Again, average is the word to note here. We're not talking about suboptimal transmission on an individual coupler. We're talking about on average. Because we know when we've got an individual coupler, it's either optimal or suboptimal. So we know what that is. It's on average that we're interested in. And so that means we're going to be doing a test on the mean. A sample of size 25 yields a sample mean thickness. So this is x bar of 3.95. This is a little bit below 4. So you can be right, perhaps, in being suspicious that the transmission is suboptimal. And the sample standard deviation is 0.08. Okay, we've got a sample standard deviation here, which is not a known standard deviation. If I had left the word sample out and put with standard deviation and left the s off, just put 0.08, this means I have known standard deviation sigma equals 0.08. But here sample means that I don't know the known value. I'm talking about s. That means I'm going to be using t in this test. The question is, can you say that you are correct? So basically, we're testing to see if we can say that we have suboptimal transmission. Optimal is greater than 4, suboptimal is less than 4. So we're going to test to see if we're less than 4. And we're going to test at a 10% significance level. This corresponds to a 90% confidence level. So let's let x be the coupler thickness. And so we want to test if mu of x is less than 4 or not. At a 10% significance level means that alpha is 0.1. As I mentioned, optimal is greater than 4, and we're told other things that we're told here is we got 25 samples, our x bar is 3.95, and our sample standard deviation is 0.08. And as I mentioned, this means sigma is unknown, so we're going to be using t. If we want to prove that our suspicion is correct, we have to put our suspicion into HA. So HA has to be mu x less than 4. And that means h naught is mu x greater than or equal to 4. And we actually test mu x equal to 4. That gives us a mean that we can use in our test statistic. Okay, our sentence is we reject h naught if our test statistic something equals something minus something over something. The something on the left-hand side is either t or z. We've already said we don't know sigma, so this is going to be t. On the right-hand side, the first something is the estimate of what we're testing. We're doing a test on mu of x, so this is x bar. The second something on the top here is the mean of this thing according to the null, which is 4.0. And then underneath, we got the standard deviation of this thing, which we know is sx divided by square root of n. We know all of these terms on the right-hand side, 3.95 minus 4 over 0.08 divided by root 25. Gives me minus 3.125. So x bar is more than 3 standard deviations away from where it should be if this claim is correct. We continue our sentence. So we reject h naught of our test statistic. T equals minus 3.125 is less than, the less comes from HA, so the direction of this thing. And then our critical value is minus, because we're looking in the negative direction, T alpha n minus 1. Alpha is 0.1, n minus 1 is 24. Look this up in my T table, and I see I get minus 1.318. Minus 3.125 is way lower than minus 1.318. So we conclude with at least 90% confidence that we have suboptimal transmission, i.e. that the true mean is less than 4. So basically we're rejecting h naught. Okay, we're quite resoundingly rejecting h naught. This minus 3.125 is quite a bit lower than minus 1.318. We see from this example that we can probably conclude with a lot more confidence, we can probably conclude that mu x is less than 4 with a lot more confidence, since that t value is minus 3.125. We could actually look to see what value of alpha is at the border of rejection. Let's try an alpha that's a good deal smaller. We had 10% above, but now let's make it, what is this, 0.25%, or 0.0025. And I see from the tables that minus t at 0.0025 with 24 degrees of freedom is minus 3.091, which is very close to the t value that we computed for this test, minus 3.125. So our sentence becomes, if we're using alpha as 0.0025, our sentence becomes, we reject h naught of our test statistic, everything here is the same, is less than minus t of 0.0025 with 24 degrees of freedom, which is minus 3.091. This is very slightly less than this, so we're going to reject h naught and conclude. We can now conclude with at least 99.75% confidence that mu x is less than 4. So we are basically very confident that the true mean is less than 4. The actual value of alpha at the boundary of rejecting h naught is probably about 0.0022, and I just guesstimated that. So that the maximum confidence interval we could have in our conclusion would be something like 99.78%. Okay, this thing is so close to this thing, I only have to increase this a little bit. So I decrease the area to the right a little tiny bit, and I would get to the minus 3.125. And I'm guessing that if I decrease from 0.0025 to 0.0022, this would be about equal to minus 3.125. Of course, there's software that can compute this. I'm just guesstimating, so it'll be something in this order anyhow. And we call this value of alpha at the boundary of rejecting h naught the p-value. Okay. Small p-values apply strong support for HA, and we saw that above here. So this particular, when we got this test statistic, the p-value we got is very small, 0.0022 approximately, and that shows strong support for the alternative. Large p-values imply the other way around, imply strong support for h naught, but remember that we can never actually accept h naught. And the rule is this: if you select an alpha value that exceeds the p-value, then you reject h naught. So one way of proceeding with these tests is to just compute a p-value, report that, and let whoever is doing the decision making decide on an alpha value. If they decide on an alpha value that's bigger than the p-value, they reject h naught and conclude that HA is correct at that level of confidence. In general, then, how do we compute the p-value? The general definition of p-value is the probability of seeing another test statistic at least as large as the one currently computed, and it's important to remember that this is in the direction of h naught. So for our previous example, the h naught, the direction, let's go back up there. Oh, sorry, I made a mistake in my statement there. Oh, yes, this is wrong. Okay, so I've written the wrong thing here. This is not in the direction of h naught, it's in the direction of HA. Oopsie, where is it? Here we go. Okay, yeah, so it's important. We're talking about the direction of HA. If we go back up to the test that we had up here, the direction of HA, where's my thing? The direction of HA is in the negative direction, so less than. So our p-value here is the probability that if we were to repeat this and compute a new test statistic with 24 degrees of freedom, that it would be less than minus 3.125, which is the test statistic we computed for this example. And from the t distribution tables, as I said, I'm guesstimating that that's about 0.0022. And so we choose any alpha bigger than 0.0022, then we reject H naught. If sigma x is known, and the test statistic then is z, which is normally distributed, then the p-value is relatively easy to compute. We compute as a test statistic z from our test, just as we did before. Something minus something over something gives us a value. And then the p-value is the probability of exceeding that in the positive direction when we have this in HA, or being less than or greater than in either direction if we have not equal to. And by the way, we use the absolute value of z in this calculation here. Even if we got a negative value of z there, but we are also going to check to see if we're above the absolute value of that in the other direction. So that's the two-sided test. And then if we have a less than here, the p-value is the cumulative distribution function at z. Z is almost certainly going to be negative here. So you're looking at presumably a smaller p-value. So if sigma x is unknown, then we're using the t distribution, and we'll have to interpolate in the t table to figure out what the p-values are. And you'll get lots of examples in the next assignment and in Laura's tutorial on how to compute these p-values. So in summary, we define H naught to be the default condition, claim, status quo, whatever. We have to remember that we can never accept H naught, we just fail to reject it. If we do fail to reject it, it may be true, but we haven't proven it. So basically you want to put in HA whatever it is you're trying to prove. Okay, so we can accept HA and conclude it's correct to a certain level of confidence if H naught is rejected. We then have to choose a value of alpha. We want alpha to be small if type 1 error is bad, but you don't want to choose it to be too small in any case. If type 2 error is bad, then maybe you choose alpha a little bit larger, not too large again, but maybe a little bit larger, 10 or 20% maybe if the type 2 error is really bad. Really the best way to correct this if type 2 error is bad is to take more samples, collect more data. Then we collect the data and compute a test statistic, and this is really equal to the number of standard deviations that the test statistic is away from the claim according to the null. And we reject H naught if that test statistic is far enough away in the direction of HA. And usually it's useful to report a p-value to indicate support for either hypothesis. So small p-values support the alternative, and large p-values support the null hypothesis. And that concludes the second part of hypothesis testing and week 10. Next week we're going to look at some of the more common hypothesis tests. We're going to look at a hypothesis test for differences in means, proportions, differences in proportions, and finally hypothesis tests on variances. And that's week 11, so that's almost the final week. After that is week 12. We'll look at linear regression. Thank you.